Okay, so let's look at practice test 1, question 2. It says solve the initial value problem by finding an appropriate integrating factor and then using exactness. So here's your differential equation: 2x y plus 1 over x dx plus x squared y plus x squared plus ln of x dy equals 0. Okay, so this is going to be my m, this will be my n. Okay, so now let's show it's not exact. So let's compute my, so m derivative with respect to y and n derivative with respect to x. Let me write it here. Okay, so my, so m derivative with respect to y, well, this will be just 2x for the m guy. And n derivative with respect to x, will be 2xy for this guy, and it'll be x squared for that, and 1 over x for the ln. So you can see they're not the same, not even close here. Okay, so now we're going to try and find an integrating factor so we can make, by multiplying both sides by integrating factor, then we're going to make it exact. So let's find the integrating factor. So recall then, we have two cases to find our integrating factor. So if h of x equal to 1 over n times my minus nx, if that's a function of x, then the integrating factor is found by going e to the integral of h dx. And if 1 over m times nx minus my, if that's a function of y, then the integrating factor is this. So let's check case 1 first. So let's check that one. So note. Okay, so looking at the 1 over n my minus nx guy, so the n is this guy up here, so the 1 over that. Then we go my minus nx, the 2x's will cancel here, and let's be left with minus 2xy plus 1 over x. And you can see there's no way, this needs to be a function of x for case 1 to work. This has a y in it here and a y in it here. There's no way you can make those y's cancel. So this is not a function of x. So therefore case 1 fails here. So again, not a function of x, of only x, hence case 1 fails. Let's try case 2 next. Okay, so let's compute the 1 over m guy. So doing that we get, so the 1 over m, nx minus my, so m is the 2xy plus 1 over x, so 1 over that. Then nx minus my, so it'll be 2xy plus 2x plus 1 over x minus this. The 2x's will cancel. It should be 2xy plus 1 over x. These are both the same now, so it's just going to become 1. And 1 you can think of as a function of x or y, so this is going to work at this one. Okay, so let me write that. So our h of y is equal to 1 here. So again, 1 you can think of as either a function of x or a function of y. So we're going to think of it as a function of y here. Now we can find our integrating factor. It's going to be e to the integral of 1 then. So let's find that here. So doing that we get, okay, so our integrating factor would be e to the integral of h of y, which is 1, so the integral of 1 is going to be integrating 1, which is y. It's going to be e to the y. That's our integrating factor. Okay, so I'm out of space, so let me erase a few things and we'll keep going. So summarizing, I have my differential equation up here, and the integrating factor is e to the y. So now we're going to multiply both sides of differential equation by e to the y. So let's do that. Okay, so now multiply both sides of differential equation by e to the y. So I'm going to multiply e to the y here, here, and here. So here's my new differential equation down here then. And this guy, oops, there should be dx here. This guy here I'm going to call, say, m tilde. I'm going to call this one n tilde. Okay, so I've labeled them. So now this should be exact. So derivative of m tilde with respect to y should equal derivative of n tilde with respect to x. Let's just check that here. Let's do m tilde with respect to y first. So note. So the derivative of m tilde with respect to y, we're going to have to use a product rule. So the 2x y plus 1 over x is the first function, and the e to the y is the second function. So it'll be derivative of first with respect to y. So derivative of 2xy with respect to y would be 2x. Derivative of 1 over x with respect to y would be 0. So it'll be the derivative of first function times second e to the y plus first function, so 2xy plus 1 over x, times derivative of e to the y with respect to y, which is be itself. I can then say factor out the e here. So doing that we get then. So factoring the e out on the right here, I would have then 2x plus 2xy plus 1 over x. I put the 2xy first, so it'd be 2xy plus 2x plus 1 over x times e to the y. Let's now do derivative of n tilde with respect to x. So let me do it here. So this guy then, well, you don't need to use a product rule because e to the y is a function of y, not a function of x. So it'll be derivative of this with respect to x. So derivative of x squared with respect to x would be 2x. So it'd be 2xy plus 2x. ln would be 1 over x times e to the y. You can see these are the same now, so it's exact. So hence we can say that it's exact. So when the differential equation is exact like we have here, it means we can find a parent function such that created the m tilde and n tilde, and that parent function equal to a constant will be the solution of the differential equation. So to find the parent function, we're going to integrate the m tilde with respect to x, and we're going to integrate the n tilde with respect to y, and then make it work. You'll see here. So let's first integrate m tilde with respect to x. So our small f, or our parent function here, will be the integral of m tilde with respect to x. My m tilde is this guy up here, so it's 2xy plus 1 over x e to the y. Now the e to the y you could pull outside the integral if you wanted to, but anyway, you're going to be, maybe I'll do that. Let me pull the e to the y out. So pulling it out, we get, so I pull it out. So we're going to integrate then 2xy with respect to x, not y here. So integrating 2xy with respect to x is going to become x squared y. Integrating 1 over x is going to become ln of x. So let me write it here. Okay, so again, integrating the 2xy becomes x squared y. Integrating the 1 over x becomes ln. Got the e in front. That's going to be plus a constant, but here now the constant is going to be some function of y. I'm going to call it c1y. This is some function of y here. We have freedom over. Okay, now we can also find our parent function by integrating our n tilde. So let's do that next. Okay, so our parent function will be integral of n tilde dy, and n tilde is x squared y plus ln of x e to the y dy. So we have to integrate this. So I'm out of space here, so let me erase a few things and we'll keep going. Okay, so that's what we have then. So we have our parent function up here. When we integrate our m tilde, we got this. When we integrate our n tilde, we got this now. We still need to integrate this one. We had it here. I broke it up now as two integrals. I broke it up with the x squared plus the ln and the e to the y. And I broke it up with the x squared y e to the y. This last one is going to require a integration by parts because you got a function of y here multiplied by another function of y. This is not going to require integration of parts. We can do this one directly because the integral of the e is just itself. So let's keep going here. So let's integrate this one. So integrating we get. So integrating the first guy, we just get this. We still have to integrate the second one. It's going to require integration of parts. So let's do it over here. Okay, so when you integrate the x squared y e to the y dy, we have to use integration of parts, which I've written here. And we're going to let the e to the y dy be the dv, and the x squared y be the u. So let me do that. So we have our u equals x squared y, our dv equals e to the y dy. So let's take derivative with respect to y on both sides here, and let's integrate both sides here. So doing that we get then, so our du dy would just be derivative with respect to y, would just be x squared here. And integrating both sides here, you'll have v equals integral of e to the y, which is going to be e to the y here. It looks like du will be x squared dy, so let's write that. So in the distance we have our v, we have our du now. So let's make the substitution now into the integration of parts formula. So doing that we get then, so making a substitution for u, the x squared y, and the v, e to the y, and the du, x squared dy, you get this. And then integrating this guy, the x squared is a constant here, consider it a constant because you're integrating with respect to y. It's going to be negative x squared e to the y then, so let me write the final answer here. So we get this then. Now we're going to substitute this now in place up here. So let's do that now. Okay, so I made a substitution over here, so our parent function then will equal this. Okay, I'm gonna erase the stuff down now, the integration of parts formula and stuff down here, it's in the way. So let me erase that now. Okay, so I've erased it. Now I'm going to pull e to the y out of this, this, and this on the right. So let's do that. So doing that we get then, so factoring the e to the y out of these terms, so you have your x squared ln of x squared y minus x squared all times e. Then you still have your c2x, so again this is some function of x here. Notice here the x squareds cancel, so this becomes then, so it becomes this, so x squared y plus ln of x times e to the y plus some function of x. So we're going to compare now this guy with the one up here. And comparing them, we can see, to make them compatible, we can actually just choose this guy to equal 0 and that one to equal 0 for our functions of x and y there. So hence we can say, so hence, so this will be my parent function then. So the general solution then will be obtained by just replacing the f with the constant here. So let me write the general solution. So our general solution is just x squared y plus ln x times e to the y equals some c. So this is our general solution. And now we have the initial value problem that y of 1 equals 0. So let's recall that. So our initial condition is y of 1 is 0. That means that when x is 1 and y is 0, we should be able to figure out what things are here. So let's work this out. So I'm plugging 1 in place of x, 0 in place of y into my general solution over here. So I've done it here. ln of 1 is 0. At 0, e to the 0 is 1. So it looks like it's going to be, looks like c is going to be 0 then. So hence c is 0. So c is 0. Let's put 0 in place of our general, the c in the general solution over here. And then we can try and solve for y. Okay, so I put 0 in place of c here, and I want to solve for y now if I can. Well, notice here actually e to any power is never 0, so I can divide both sides by e to the y, so let's do that. So dividing both sides by e to the y, I just end up with x squared y plus ln of x equals 0. I can subtract ln, divide by x squared to solve for y. So solving for y we get then, so we get then y equals negative ln of x over x squared. So this should be the solution to the original initial value problem that we were trying to solve at the beginning. So let me actually write up the original question again because it's related actually to question 1. So let me write it up here again and let me explain. So let me erase a few things here. Okay, so here was our original question we had as our differential equation. We had our initial condition y1 is 0. We found that this was the solution. And I'm claiming this is related to question 1 on the practice test. So in particular, I want to solve this for dy dx. So let's take, let's take this over here. So doing that we get then. So I get this then. Now I want to get the dy over dx on this side, so let me divide both sides by this guy, and divide both sides by dx. So I want to get dy dx by itself, so doing that we get then. So solving for dy over dx we have this then, and this looks almost like question 1. To make it look exactly like it, let's multiply top and bottom by x, so doing that we get. So multiplying top and bottom by x, so it'll be x times 2xy be 2x squared y, x times that will become 1, and put the x on the side here. Now this is the same as number 1 differential equation, so the question number 1. Okay, so we know this is the solution up here, okay? So recall now, using Euler's method in question 1c, we found that y of 1.1 should be approximately equal to negative 0.094. But now we have the solution exactly up here. So we can check how close our approximation is. So let's evaluate our guy up here at 1.1. So let's do that. So now we can find the actual value at 1.1 because that's our solution up here. So I'm going to put 1.1 in place of x here and here. So I got minus natural log of 1.1 over 1.1 squared. And let you check if you put that in your calculator, it's roughly equal to negative 0.079. So these are fairly close, these answers. So just to summarize, over here was the answer from Euler's method, which was negative 0.094. So that's our approximate answer. And here we found our exact answer was negative 0.079. So that you can see they're pretty close. Also in question 1, we used a slope field to graph an approximate solution curve passing through y1 equals 0. So you can check if you graph this, you can compare it against the graph we had in question 1. I won't do it here. I'll let you check that. They should be pretty close. Okay, so we're done with the question, so let's leave it there.